Hello, my name is Alex. I'm an AI field engineer at Graphcore, and today I'm going to go into a high-level overview of the IPU architecture from a software perspective, and we're going to have a look at a simple addition example running on the IPU using Graphcore's Poplar C++ framework.
Okay, welcome once more to this introduction to Poplar, and we're going to have a look at C++ programming on the IPU. So first of all, what is Poplar? Poplar is Graphcore's parallel programming framework which targets the IPU. It's designed to be simple but powerful, allowing close to the metal development for maximum performance whilst also being general purpose. The Poplar graph, which represents our computation, is made up of the data, the variables in the graph which we want to perform some operation on, the compute tasks themselves, which we call vertices, and the edges that connect them. The data is stored in the graph in fixed size multidimensional tensors. So for example, here we see 3D, 1D and 2D tensors. Variables can be distributed over multiple tiles. So for example, a tensor could be put onto tile 0, or a large tensor could be split up and slices of this put onto different tiles. So vertices. A vertex is a small computational task. So for example here we want to create some addition vertex that takes two floating point numbers, adds them up and returns the result. So on the left here we see we're just adding 1 and 2, and of course we get 3. The codelet to represent this, so a codelet is a small snippet of C++ that tells the vertex what to do. That's shown on the right, where we take two inputs, both floating point, x and y, and our output, z, also a floating point number, is just the sum of x and y. So each vertex is associated with a codelet like this. A vertex runs on a single tile, so in order to get the best performance by taking best advantage of the hardware available, we want to run many vertices in parallel. So going back to this Poplar graph, in this case we have 4 input floating point numbers in a tensor, and our vertices are addition. They're just going to add up various elements of the tensors. So the first one we see here adds up all 4 elements, the second one adds up just the last 3, the third one adds up the last 2, and the fourth adds just the last 1. And these are then stored in the output tensor we see at the bottom. So we notice with these vertices that they all read from the same tensor and they all write to different elements of the output tensor. So there's no data dependency there. There's no reason why we can't run these in parallel. So we can put all of these into what we call a compute set. So a compute set is a set of vertices, all of which can run in parallel. And Poplar verifies that the compute set is free of any race conditions or any other reasons why we couldn't execute these in parallel at the time of execution. So to execute our compute set, so to run all of these variables in parallel, there are 3 main steps. First, there's an exchange, so we transfer the inputs to these vertices from whatever tile they're on. We perform the computation, so run all these vertices in parallel, and then we exchange at the end to transfer the outputs to wherever they need to go next. In between these stages, there's what we call a sync. So a sync is where all of the threads synchronize together to make sure that they've all finished before performing the next stage. And all of this exchange code is generated in the background by Poplar. Finally, we have data streams and control programs. So a data stream is for transferring data between our host memory and our IPU memory. So for example, we could send from the host to the IPU some batch worth of training data to perform a training step of a model, and we could send back the results of some computation back to the host. Control programs specify the sequences of operations. So these could include statements to execute a compute set, copy to and from a data stream to send data to and from the IPU, and also control flows. So for example, conditional statements and loops. And each tile holds a copy of the control program which they all execute synchronously. So all of these elements of our Poplar graph are all compiled together to form our Poplar executable. So we have the Poplar graph itself with our vertices and our variables. We have the codelets, which contain the code to tell the vertices what to do. We have our data streams to send data in and out of the IPU, and our control programs which tell the IPU in which order to perform each task. These are all compiled together into our Poplar executable, which must be compiled before it can be loaded onto the IPU. So, going back to this graph for a moment, this is what we're going to have a look at how to write the C++ code in order to perform this operation. So let's take a look at the code that runs on the host first of all. So the first thing we do in our main function here is create what we call a device manager. This allows us to request a device on the system, so an IPU device. And here I'm going to create a Poplar device and point this to IPU index 0. So this is the first IPU of the many IPUs on this system. I then create a target which allows our code to attach to this device. Now we create a Poplar graph. It's empty for the moment because we haven't added any vertices or variables to it, and that's what we're going to do next. But first we must point this graph towards our codelets file, and this is where we put the snippets of C++ code which tell the vertices what to do. So let's take a look at our codelets for a moment. So here we have a class. I've called it SumVertex because this is a vertex that will just perform the sum of some numbers. And it takes in an input, which is a vector of floating point numbers, and then produces an output, which is a single floating point number. So our Boolean compute function here tells us what the vertex is going to do. And we start off by defining our output float as 0, and then we iterate over the elements of our input vector, adding each one to our output. So the output becomes the sum of the elements of the vector. Okay, so back to our host code. Before we can run this vertex, we need to put some data into the graph. So we create two variables here, v1 and v2. These are both 4-element floating point tensors.
And then we loop over the elements of both of these tensors, and in each case we map the ith element onto tile I of the IPU.
Now we create a control program, which is just a sequence of steps to run on the IPU. The first step we're going to do here is to initialize our input tensor for the vertices. So I create a constant tensor here, C1, which is 4-element floating point tensor with values 1, 1.5, 2, and 2.5, much like we saw in the diagram of the graph. It's a small tensor, so there's no problem with mapping all of this onto tile 0. And the first thing our control program is going to do is copy the values in the tensor C1 to V1. And V1 will then form the input to our vertices. So now we create our compute set, inside which we'll create 4 vertices. So looping over our index up to 4, each vertex we point to our SumVertex class, as we defined in the codelets file. And each vertex will point the input vector to a slice of our tensor v1. So when I is 0, our slice will be the entire tensor, all 4 elements. When I is 1, we'll just add the last 3 elements of v1. When I is 2, it's the last 2 elements. And when I is 3, it'll just be the last element of v1 that's input to our vertex. And then we connect the ith element of our output tensor v2 to the vertex I. Finally, we map our ith vertex onto tile I on the IPU. We note here that the output tensor element is on the same tile as our vertex. However, of course, the tensor v1 is spread across multiple tiles, so there will be some amount of exchange which goes on when executing the compute set. The next thing we do is we add to our control program a statement to execute our compute set. The final step in our control program is just to print the tensor v2, which is our output, and this will involve copying the values back to the host so that they can be printed to the terminal. So now our program is constructed, we now create a Poplar engine. Now the engine is what manages the running of our programs on the IPU. So we feed into this our Poplar graph and our control program. And then we load our IPU device. The final step now is to tell our engine to run our program. Now the index 0 here refers to which program to run. In our case, this is redundant because we only have one program in our engine, but we could feed in a vector of many programs. So for example, we could run the first program, and then in a loop we could run another program a number of times, and so on. So the next step is to run our code. So I have here our two source files, the host code and the codelets which will run on the IPU. So now I'm going to just compile our host code with standard G++ and link it to the Poplar libraries. We note here that we don't need to manually compile the codelets because these will be compiled at the time of execution by the Poplar compiler. Okay, so now we've compiled our code, we can run it. And we see here that, as expected, the sum of 1 plus 1.5 plus 2 plus 2.5 is indeed 7, so that's our first vertex. The next vertex takes in just the last three of those numbers, which gives us 6, and so on.
Okay, so now we see how quick and easy it is to run a simple example on the IPU. So what have we covered? Poplar graph is made up of variables, the data on which we perform computations, vertices, the computations themselves, which are defined in C++ codelets, and the edges that link them together. The vertices are then encased in compute sets, which run sequentially on the IPU. So to follow this tutorial and others, head to our GitHub repository, and you'll also find other developer tutorials and other resources at graphcore.ai/developer.